Good morning, everyone. Welcome, friends. This is the EasyPower Tuesday Refresher Series. My name is Jim Chastain. The primary purpose of this series is to cover a bit more depth on specific aspects of the tools and its use, and highlight some features that may not be covered as often as we should. So I welcome everyone to the discussion. Now, as many of you know or currently use EasyPower are aware of the modules that are involved in short circuit and arc flash studies, I just wanted to highlight that this involves the database editor, the short circuit module, PowerProtector, and then the arc flash. I'm leaving off the optional smart PDC for no particular reason, but our emphasis is going to be on PowerProtector, and the point is that all of these modules interact, and we're right at the crux when we're starting to talk about protective device coordination, where the overlap can be significant, and it's important to know how these different modules interrelate at that juncture. So this is what we're going to be covering today. And basically, there's a lot of ground here that, like I say, I won't be going into depth, but I do want to touch on each of the topics. And if I miss something, by all means, at the tail end, please remind me, and we can kind of circle back and pick up anything specific that is missing. So again, welcome all. And what I'd like to do is to start, as we frequently do, with a poll question. So if you would, please help out by participating in the poll, which we're going to start off by asking, how frequently do the studies that you do require protective device coordination? And so if we can get some feedback from folks, it would be helpful. And again, appreciate your participation as much as anything else to make sure we're covering the ground that we need to cover in the discussion. So here's how people are coming up with feedback on this topic, which is good because I think we're going to be spot on as far as where we're taking the discussion. And then secondly, what areas of coordination do you have questions about? And again, we're trying to bracket as many people in this discussion as we can, and we will have questions at the tail end, or time for some questions. May not be able to get to all of them, but certainly where we can and where we can illustrate a better understanding of the tools, we'll try to incorporate that. All right, so appreciate everybody participating. Here's how things stack up with that response. All right, so let's kind of jump into this. Now, what I'd like to touch on real briefly is a topic that's actually part of the short circuit options discussion, and I neglected to touch on this last week, and because it does impact our discussion on protective devices, I want to touch on this, and I would encourage you to kind of follow up on the specifics, especially where it may impact you or it may have its importance to your particular work. So, and that topic is the calculation of X over R. And so when we go into the tools, you'll see that in short circuit options we have three choices for X over R calculation methodology. And if you go into the context help button or window, you'll see a description of what each of these methods affords. And what I would encourage you to do is to go through an exercise comparing each of the methods on a circuit that you're familiar with and see which seems to work best for you. And it turns out, and I'll kind of touch on this when we get into the tools, it turns out there is differences. The ANSI standard was developed primarily before computers were that that widely used in this area, and so it's an easier methodology to handle with hand calculations. You'll see a lot of alignment between the ANSI standard and the non-standard until you get to a little bit of a different time as far as the fault timeline, that being momentary versus interrupting versus 30 cycle. But what I would encourage you to do is to look at the CCM method, which again is much more complicated in terms of the way the ratio is calculated. So when I jump into the tools, I'll kind of show you where this is and what I would recommend in terms of a little bit of a test to look at the differences yourself. Very frequently when we get into talking about protective device coordination, many people seem surprised that sequence of events, as valuable a tool as it is, has been available for several years now, because it answers a lot of the questions that people have in looking at the tools, the tripping sequence, and which faulting device or which protective device is actually in play when it comes time for both mitigation and for coordination. So I'm going to spend a little bit of time on sequence of events. Basically, there is somewhat of a procedure to kind of become comfortable with. First of all, you need to be looking at currents. You need to set up for a balanced three-phase fault. You need to fault a single bus, and then select the sequence of events icon. And then, as important as anything else, you need to understand how to generate a report so that you don't have to always look at the one-line diagram. All right, so let me jump into the tools and let's kind of walk through some of these areas. And I want to set my windows up so I can pay attention to what the list I just gave us. All right, so here's a typical radial system, and what we see, if I kind of come down here to a remote bus, several different things. First of all, the X overall calculation. I go into the Short-Circuit Focus, I go to my Short-Circuit Options tab, and under Control, I see in the top right-hand corner 3 methods for calculating X over R. And as I mentioned, anytime you're in one of these dialog boxes and you have a question about it, probably the first place to go is to the Help screen, because that will take us to directly to the section of the user's manual that describes specifically what's being required. And here's where you'll find the discussion on the X over R calculations. So what I recommend is to try the following example. So let's leave it in ANSI to do my calculations. Let's go back to my tools. I'm going to first of all, I want to create high voltage momentary report, low voltage. I'm basically going to be looking at low voltage. So high voltage and low voltage, both half cycle and 5 cycle, which is what's indicated here, in either medium format or detailed format, and then the 30 cycle report. The point being, as we generate these reports, I'm going to fault all the buses. And as I do that, the window reduces in size because I have all these reports stacked up here at the bottom of the screen. And what I want to do is look at the low voltage momentary report for the momentary timeline, and then the interrupting report. And what we're looking at is the X over R calculation. So you'll notice even between the momentary and the interrupting, for the ANSI calculation method, the X over R ratio changes. What I would suggest is to export both of these to Word, save that file for comparison, and then go back to the folder, Short-Circuit Options, Control, and pick either Standard, Complex, or Characteristic. Apply. I'll go ahead and fault the bus, even though it looks like it did a recalculation for me, and then look at my windows again. And if I look at my low voltage momentary, and then low voltage 30 cycle, well, interrupting as well. You're going to see that the X over R ratio is different from what we saw in the ANSI calculations. And so, again, it's going to vary based upon the timeline you're talking about and your particular circuit requirements. And there could be advantage of one versus the other based upon what you're trying to do. So I throw that out there because the X over R calculations is actually significant even when we get into protective device coordination. And let me just kind of leave that one where it stands. Okay, start with sequence of events. I've completed my one-line diagram. I have, for all intents and purposes, calculated short circuit currents. I'm going to fault the buses, and I'm going to get rid of my reports just because I don't want that window to continually change on me. All right, the point here is what happens if this particular bus faults? What happens to the tripping devices upstream? So I'm going to go to Coordination Focus. I'm going to look at currents, not energy. I'm going to three-phase bolted fault. I'm going to fault a single bus. And again, because I didn't have a bus selected, it faulted everything, so I'm going to go back and fault this single bus here. And what I see are branch currents for that particular fault. Now, sequence of events is this little icon right here in the center that illuminates after I go through that little process I just went through. And if I click on that, it will show upstream from that bus all the tripping devices that are affected by this fault. And what this tells me is that when this bus faults, this breaker upstream will trip in 50 milliseconds. The main breaker on this particular bus will trip in 340 milliseconds. If I go up to this relay will trip in a little over a second. This relay will trip, well, it won't trip because it's stuck at 1,000 seconds. And this one is stuck at 1,000 seconds, indicating it will not trip, and it's flagged red because there's not a time difference between it and the next device downstream. Now, as I indicated, it's not a bad idea to show this information so you don't have to keep zooming back and forth in the one-line diagram. Show this information on a report. I get to that report under the PDC Options icon, create sequence of events. So I'm in the General Options, right-hand column, bottom checkbox, and Apply. Now when I go back and fault this bus again, and again I just want to do one bus, I'm going to see a report now that tells me exactly what I saw. And it's showing that there's some out of sequence, and you can see it right here, where this trip time, well, I can display the trip time both in absolute time from fault or in differential from the upstream device. Now, a couple other things kind of show up in this. First of all, the trip sequence or the breakers in play may be more complicated than we expect based upon how complex our circuit is. A couple of ways to kind of deal with that. First of all, if we kind of come back to our diagram, as I fault this bus, the way I have it selected, I'm only showing the localized current. One of the capabilities, and this is an overlapping option in both short circuit and protective device coordination, is the ability to show branch currents or remote current and voltage on other devices. And because it is overlapping, there is an icon in the coordination focus banner that shows the short circuit options. And what I'm referring to is showing all remote voltage and current for a single bus fault. So as I apply that, we can see that my display changes. And so now, based upon that one bus that we had selected faulting, here, this is showing me what the effect is on this bus over here. So if this motor faults, you'll see that the voltage on this bus, which normally is going to be 100%, drops to 0.9596 per unit. And during the initial half cycle, which is what we're looking at, some 22 amps is contributed from this motor, some 10 amps, I can't read my number, 100 amps is contributed from here. But the point is, there's a lot of impact on the system for this relatively benign fault, and it will last until we're able to clear the fault. Now, you might say, okay, that's pretty cool, Jim. What's it look like for the whole system? Well, if I click somewhere off in the white area, so I don't have any particular bus selected, I fault all the buses. Now I'm going back to the individual branch currents. If that bus faults without showing any remote impact, the significance or the advantage is now I can go to my sequence of events report, and now it does show me what the contributing sequence is for every bus in the system. I maintain this is a good way to kind of double check and verify how much of a coordination problem you're going to have, because you can see what's out of line for each bus. And in this case, you can see the relays are pretty much offending no matter where my fault is. They're out of sequence. All right, so that sequence of events, I find it's extremely valuable in terms of troubleshooting faults and in coordination, because you're kind of pointed to where you need to pay attention. Very frequently, rather than, you may be adjusting the wrong breaker, bottom line, if you're trying to mitigate incident energy. Okay, so that brings us to TCC plots. And let's kind of come to another part of this one line, which is very common in terms of areas that give people problems, and that is where we have a voltage transition. In this case, I have a 208 volt panel and a string of protective devices above it. And when I do my short circuit calculations, I can see that I get very high incident energy at this bus, even though current-wise I'm seeing relatively low current compared to all the other bus faults that were indicated. So the question is, how can this be, or is that incident energy real in terms of a 208 volt system? So a couple things we're looking for. Let's first of all plot this particular chain of events. So we're going to go to coordination. I've selected the elements I want to plot. I'm going to plot the TC curves. And there's a couple things that just kind of show up. First of all, here's what I've selected, the one-line diagram. You can notice there's an inset over here along with my TCC plot. Now, let me just kind of talk about TC curves. So this is time current characteristic curves, and the only difference between them and most other curves we look at is that this is on a log-log scale, which allows us to put a wide range of values, but it's significant because I can plot all of these devices on one frame of reference and see how they interrelate to each other. So for starters, I'm going to take off my little title block at the bottom, which is controlled by these check boxes at the top, to give me more room on my display. And what this is plotting, on the horizontal scale is current, on the vertical scale is time. So if and notice this little right down here in the very bottom of the screen is a cursor readout from wherever I'm placing my mouse. For this particular dot, for where the pointer is, represents 1,747 amps at 33 milliseconds. So if I have a fault in this that occurs at this point, say even a 2,000 amp fault, if it only lasts for, let me kind of scoot it up to 2,000. If it only lasts for 12 milliseconds, it won't engage the breaker, which is the first one that's indicated upstream. It may cause a perturbation in my system, but it won't pick up any of the protective devices. If I have in this case, a 200 amp fault, and it lasts for hundreds of seconds, it also will not pick up any of the protective devices. Whereas if I have a current spike that's 37,000 amps, and it lasts for a second, any number of these protective devices is going to be activated, and so I'd expect to see systems drop off. Now, you'll notice that there's a color coordination. The easiest one to see is this fuse is kind of magenta or red, and it correlates to this curve here, which if I look at is, of course I got to pick out the right label. Is this fuse, and so I've selected in my options for my plot to coordinate the breakers or the protective devices with their curve. Okay, so what's going on? First of all, let's look at the fuse itself. The tool allows us to open up the dialog box for a particular element either by clicking on the one-line diagram or clicking on the chart on the plot. So if I double-click on the plot of this curve of the fuse, it opens up a temporary fuse switch dialog, which is this fuse, and there's several things that are available from this display which are common to all protective devices. First of all, there's a tripping TCC clipping that we've set up to trip or clip on momentary current. We can select either interrupting or 30 cycle. There's also the ability to indicate a tick mark on either momentary current, interrupting current, or 30 cycle current. So we've selected momentary current, and let's kind of come over here and look at that. So what I've just done, here's FS2, and if we look at this, it's indicating a tick mark at 10,040 amps. And if we come back here to our short circuit, here's our tick mark that we indicated as 10,040 amps. Now that's indicated up here on the tick mark, but let me kind of show you something here. If we look at the scale that we're on, this tick mark was in the 480 volt bus or 480 volt environment. If we look down here on the scale that we're actually indicating, that tick mark is actually, because we're multiplying by 100, here's 100,000, so 160,000, so this 10,000 amp fuse won't trip until we get 600,000 or 600,000 amps, which causes problems. All right, so let's talk about what the problems are. If we fault this bus down here, this panel, you'll notice that all the curves are stripped back because they're clipped. Again, we're looking at the maximum current now that's being driven, and you can see that my fuse is way up here as far as its pecking order. And so in terms of what's going to trip on this particular fault, here's panel 1 main, here's panel 1 row 7, which is the feeder going down to this transformer. And the tool, if I right-click in the bus or the protective device and insert arcing tick mark, all right, I pick this particular curve because it looks like it's the one that's most downstream. I right-click and I insert arcing tick mark. This shows me that we'll get a fault here at 1,311 amps arcing current. It's showing this is tripping at 100% arcing current. Now there's a couple other things perplexing about this. For starters, this particular fuse is in the 480 volt section, 480 volt part of my system, and my load that's actually faulting is in 240. And when we look at this, if we look at the incident energy, we can see this is very high incident energy. The question is it real? Well, 5,000 amps, that won't be extinguished for some, we kind of look at where the tripping point is going to be. So this particular breaker won't extinguish or won't clear, looks like, for 7 seconds. So the answer is, yeah, this could be a problem if we've got that much current faulting or arcing for an extended period of time. Now in reality, testing has shown that voltages below 125 kVA at 240 volts won't last more than a half a second, and so that's one way to at least artificially or to show a more realistic estimate of what these currents or energy will be. But in reality, why isn't something going on inside of this panel here? So let's kind of go back and answer that question. The question I'm exploring is, why doesn't a protective device do something in this particular fault in that remote panel? Well, this is a problem with many existing systems, older systems, and what we go to find when I come back to look at this panel, it was actually set up with main lug. So, all right, so one solution might be to put in a protective device, say a fuse, and if we pick out, say, a generic fuse, and let's set it up for 100 amps, that might be one solution. Another solution or another fact is, well, when we get into short circuit and we look at the short circuit options to calculate instant energy, are we including or excluding the main? Well, we've set this panel up, we set the whole system up, because this is a global option, to exclude the main. So even if I put a fuse inside this panel where it can be bridged with a plasma ball inside the panel, it's not doing the trick. So another suggestion would be to move the fuse outside, or at least have a barrier between it and the panel we're trying to protect, in which case we could include the effects of that particular protected device. So now by doing that, if we go in and fault this particular bus and look at the incident energy, we have a much more realistic or acceptable level of energy. How does that look in our coordination focus? If we go back to plot the curves on the same bus or the same leg, now we see we've added this fuse. Here's the main on the panel, and now when we have a fault, I can insert the arcing tick mark, and it's telling me that it's still not the device in play. And rather than plunking away at that, what I would suggest doing, this is a good point for sequence of events, because it's not clear to me that I'm going to look at current, fault that bus, just the one bus, and then look at our sequence of events. Okay, so the fuse is the tripping device, and that's why we're getting a better result. Okay, so where does that leave us? So we've looked at sequence of events, phase and ground current. Let's look at the same plot, and let's see if any of these devices have it's not even clear that they do. If I want to look at the phase and ground current fault, I need to, one, select a fault that has a ground included, and then second, between my phase and ground selector, view the ground plot, and then view both. And at this point, I don't really have a separate ground protector, so let's go back and find another bus that does. I can tell already we're going to be running along on this particular topic, so let's let's fault this bus. Let's use a phase and ground fault. Show phase and ground. Go back and look at okay, so we have a ground setting here. It's not opening anything. Other than that, that could be the problem. Well, rather than waste time setting this up, the point I wanted to emphasize, and so I kind of did a poor job of setting up the example. The same curves can show both ground and phase faults and coordinate ground settings. I have to use a line to ground fault or a fault that has ground in it, and then I have to display the ground coordination, and it will show, in fact it's going to be on here somewhere, I just need to look for it. It will show where the ground settings are. Okay, just before I go back to this one leg that I already have successfully displayed, I want to show a couple things here. Very frequently we want to display a time difference between the breakers. So the way we do that is we'll fault the bus, indicate, it's really tough to do on a vertical bus. There we go. Let's fault this bus. Let's see our arcing current. So I right click, insert arcing current. I want to see at this particular current, which is where the maximum current that this bus would draw during an arc, and what the time difference is between my respective devices. I select one curve, hold down shift and select the other curve, and then insert the difference, and then center this little dual-ended line arrow right over that current. I can do the same thing between the next breaker up and the relay. Select the relay, create the differential between the two, center it over my arcing current, and so now I can see what the difference is between the clearing time on the downstream breaker, the pickup time on the next breaker up, the clearing time, and then the pickup time on the relay above that. Okay, custom tick marks. If I want to put in, let's say, any tick mark, and again, these are the tick marks that are there are based upon the breaker's rating or settings. I can put in a short circuit tick mark any place I want, and so at this one, if we say we wanted something at 5,000 amps, if I click OK, it shows up at 5,000 amps right here, and I can use that and its location is going to be dependent upon whether I indicate it's momentary, interrupting, or 30 cycle, and it moves it up and down on my display. We talked arcing tick mark, 85% and 100%. One of the things the tool does for us automatically is compare 85% versus 100% arcing current. And that comes into play when we have a breaker adjusted. So I've hovered over this curve, which gives me the dial settings. And again, I'm looking at BL3. I can open up the curve by double-clicking on the breaker on the one line or on the curve itself, and then I left-click and drag to change the settings, and it's showing me what adjustments I'm changing as I go. You'll notice as I adjust it such that the arcing current falls into the vertical band of the curve, the tool automatically adjusts to an 85% arcing value, because that becomes the more restrictive or the worst case in terms of calculating incident energy. So if we look at the incident energy over here for this bus, which is the one I'm faulting, you can see that just by backing off that set point a little bit, that we have a better incident energy, because the breaker can use, or the tool can use, the 100% arcing current to ensure clearance. Problem is, as I do that now, I have a potential miscoordination between these two breakers, this breaker and the one upstream. So at that point, I want to go through the same process with this breaker and make an adjustment there to make sure I maintain coordination. Now, when all this is said and done, what we really want to end up doing is generate a report, and so this will give us a coordination report then based upon the settings that we have selected for these particular devices. Okay. So we talked about the X over R calculation, the sequence of events. We talked about the TC plots. There are ways and parameters you can change, customize the title block, put your logo, put your name, include the date, and a host of information that I'm not going to get into details here, but that allows for a nice display where it can be printed either in a printer or in a PDF file and displayed on a single page or on 2 pages, all of which, you know, goes to the look that you want to maintain for your organization. We talked about the temporary dialogues. So as I click on a device in the one-line diagram, it opens up the temporary dialog page and allows me to make adjustments. As we make these adjustments and apply them to the circuit, they won't be carried back to the one-line diagram until I close and then confirm that I want those adjustments to be taken back to the one line. So they're only in a temporary form as long as we're in the coordination module. We talked about custom TC curves. Actually, we talked about putting in tick marks. We can utilize this new curve insert icon at the top to produce a curve for any particular device we want to pull out of the library or describe on a temporary basis, both AC and DC. We could call up a generic curve, in which case we could actually have a custom device that we've created previous to this and stored in the library. Or we can either shift the curves if we pick out a specific curve. We can shift the curves. Let's pick out my transformer curves. We can shift the curve right or left. So let's pick one of these out and see what we can do with it. So if we look at this, yeah. So what I'm doing is I'm shifting the curve by some percentage point right or left based upon whether it's positive or negative. And that ends up being valuable in considering other devices or impact upon my system if I want to kind of punt and start over with a different manufacturer or type of breaker. Temp dialog access, arcing tick mark we talked about. We've indicated where the 100% and 85% current is automatically calculated and used for incident energy, how that's impacted by the vertical band, and we talked about how to illustrate and display the remote current and voltage. So that covers probably the extent of what I wanted to do today. Sorry I ran long. Appreciate everybody for attending. Make sure, if you got more detailed questions like this on any of these topics, you're more than welcome to contact tech support at easypower.com by email or phone, and we'll try to help you as much as we can. Appreciate everyone attending and supporting EasyPower. We'll talk to you next week.